All right, thanks everyone for joining another water talk today. It's 12 o'clock Eastern time here, so we're gonna get going with today's water talk titled Understanding and Using System Curves in Hydraulic Modeling. I am Youssef Alfaham, one of your hosts for the day. I am a solutions engineer with Autodesk, and with me today is Patrick Moore, who can introduce himself. Patrick.
Hi, everyone. Hello. I'm one of the technical support people here with Innovyze. I've been here about 7.5 years. It's about 15.5 years as a consultant before that. Love doing these kind of things and looking forward to talking with people today.
Yeah, Patrick is extremely experienced and he knows a lot about today's topic. So we're very grateful that he found time to give us this opportunity here. And just a few housekeeping items. So when it comes to questions that you're going to have, please put them in the Q&A tab. The chat is not going to be for questions. The chat is going to be for communications between attendees or between attendees and panelists. But we're only going to be answering questions in the Q&A tab. The other thing that I wanted to point out are the upcoming water talks. So we have November 1st and Info 360 plant water talk, and on November 15th, an info drainage water talk. And then finally, we're going to wrap up the year on December 13th with a end of year recap. And that pretty much covers everything on my end. So Patrick, I'll pass it on to you to begin the technical content.
Awesome. Thanks, Youssef. Well, welcome, everyone. We have a great topic that we're talking about today, system curves. What a fantastic concept that really can help and covers a lot of things. Obviously, it's a very broad topic. We get a lot of questions on this in technical support. It's one of the reasons we wanted to cover this again. Just to kind of briefly go over what we're going to cover today. One is just a quick review of some key concepts in system curve theory and key points of understanding, because if you don't catch those key points, I think you can miss some very important things. Then how to run system curves in Infowater Pro. Basically, it's going to be the same way if you're in Infowater. And then some practical applications. Hey, now that I have my system curves, how can I use that? Or, one of the main ways people use those to guide choosing a pump. And then also, something we get a lot of questions on, hey, closed zone system curve analysis, those are kind of their own unique thing. And so we're going to talk about some tips and tricks for that. And then, hey, the Infowater Pro pump curve tool, how you can use that, how it actually will show you where your system curve and your pump curve, when your model is running, where that pump is hitting. And why that can be very useful in using that for basically telling you, hey, this is why your pump is operating where it is. We'll get into that later on. And then lastly, and very importantly, how you can use SCADA data to not only validate your pump curves and system curves, but also use that to help guide you and give you some information on, hey, where are my pumps really operating? So when I'm making those pump curve choices, in that thing when I'm trying to make that good decision on, hey, where are my pumps normally operating? So I'm trying to maximize that efficiency when I'm using that system curve and overlaying that with my pump choices, so I can best choose, hey, where do I really want to maximize that efficiency? That's why that's important. So we do have, in the past, we had a system curve presentation that we did. And so I'm going to have some links in here to that. There's a blog post as well as the presentation slide, because a lot of that material, some of that we're going to cover today, some of it we're not. And so just so that you have that and have a link to that, we often, when people ask about system curves and have questions, we'll point them to this and, hey, look at that first. But I'm going to have a link to that just so that in case you want to review that, I highly recommend taking a look at that, because there's a lot of good information there. So let's jump into this, and take a look at just kind of some of that system curve theory. Obviously in a basic system here, you're going to have, a pump station, that I've got, and that's what I want to run my system curve on. And so there's something on the suction side that's controlling the hydraulic grade line that, yeah, I've got a tank that's there on my system curve. Let me find my mouse here so that you can actually see this here. The on the suction side, I've got the minimum water level on there, and I've got a maximum water level, and then I've got a discharge tank, a receiving tank, and that receiving tank has got a minimum and a maximum water level as well. And I obviously can have variations on this. I may have a system where I do not have a tank on the discharge side. That's kind of what we would call a closed zone. Hey, it's a pumped only system. Or I may have a system where I pretty much don't have a tank on the suction side and I'm just pumping from that. Or I might have just no tank on the suction side, no tank on the discharge side. And that's all that's there. But something is controlling the hydraulic grade line, but understanding your system. In a lot of cases, though, most of the time, generally, you do have a tank on the suction side and do have a tank on the discharge. That's most often what you're going to run into. But generally, understanding, hey, this is what I've got, and knowing what that's there, this is what's there. So generally, just kind of generalizing a system, that's kind of, hey, this is my system. And so understanding that, and that, hey, there can be some variations, but knowing what's controlling the hydraulic grade line on both the suction side and in the discharge side and how that can vary is going to be very, very important. Okay. And so what is a system curve? Basically, a system curve is a curve that's going to represent the energy required to push water into a system at a pump facility. So and that energy is generally going to increase as the flow increases. Why? Because the head loss is going to increase. And so this analysis is a station analysis. It's not a pump analysis. You don't do a system curve for pump one, a system curve for pump two, a system curve for pump three. It's a analysis of the entire station. That's oftentimes not fully understood, but it's an analysis of, hey, because I'm pushing water in through this entire station. So that's not a pump analysis, it's a station analysis. Okay, so that's very important to understand. Also, lastly, a system curve is highly dependent on the boundary conditions. So when we're looking at, hey, I've got a tank that can fill or drain, and I've got a tank that's receiving that can fill and drain. If those tanks are full or empty, that's going to have a huge impact on what that system curve is going to be calculated on. And so understanding what those boundary conditions are, is there demand? Is there not demand? What other facilities are operating, or am I the only thing operating? All those things are going to impact the boundary conditions, and those boundary conditions are going to impact what is going to happen in this analysis. Because those boundary conditions can vary, there's oftentimes going to be, instead of just a single system curve for a pump station, it's usually a range or a family of curves. And so understanding that as well is very, very important. Hey, it's not just a single system curve, but a range of system curves. So if I can find the highest system curve and I can find the lowest system curve, all the other system curves that are possible are going to fall in between those. And so those two become the most important ones. Hey, what are those? If I can find those, that's the most important ones that I need to analyze, because all the other ones are going to fall in between. So here's an example. In here, I've got the green curve. The green curve is representing my highest system curve, the upper bound, my maximum system curve, and the red curve would be representing my low system curve, the lowest system curve that I could possibly get. And then, the purple curve here is basically a representative pump curve that you've got. And if you notice on here, now you'll forgive me, I'm looking off on the rec because that's where my presentation screen is, or my camera is right in front of me here. But on the line of the pump curve in between the green and the red, along that line is the only place along that pump curve that the pump could ever operate, is in between on the pump curve along that line, because the pump can only operate along its pump curve, right? But it only can operate in between those two possible system curves, because that's where a pump operates, where the pump curve and the system curve intersect. So obviously, as the system changes, it's going to be somewhere in between that maximum and minimum curve, and it's going to intersect. And where it intersects along that pump curve is where that pump is going to be operating. And so, basically defining where are those and finding those upper bound and lower bound curves is going to be the magic, right? That's the important part. You've also got, right at zero flow, that's going to be your static lift. That's going to be the minimum amount of energy I need to put in to my system before I can even start pushing water into the system. If I've got water at this level, another, at this tank, and I've got to go to this tank, that difference in water levels is my static lift that, hey, that's my minimum energy that I've got to put in before I can start pushing water in there. If I've got demand, and sometimes I've got water, I'm supplying from this tank down and I've got head loss down. So sometimes that static lift can get lower than what I expect on that red curve. And that's sometimes what can happen, but we'll see that there. So let's go to our next slide here. So how do people use system curves, right? So, hey, we've got a family, it's a measure of energy. So why would I care, right? So obviously, hey, because they do show us, hey, this is where our pump can operate. That's one reason why systems are very important, because that's where my pump operates. That can tell me a whole lot of important information, both in my model as well as in the real world of like, geez, why is this pump doing this? The system curve and knowing the pump curve together tell me everything about how that pump is going to operate, as well as if I'm deciding, hey, is this a good pump choice or is this a bad pump choice? Knowing those two things together is going to tell me everything about what that pump is going to do. Again, secondarily on an existing pump, being able to evaluate, hey, why is it doing what it's doing? Or, is there something wrong? Is this pump oversized? Is it undersized? Why is it doing it? Knowing that and having that system curve, that's often a very useful tool, how people use system curves to basically do those kinds of things. And then lastly, probably one of the most important things is to give yourself a very good guide when, hey, I'm now got to either put in new pumps or I'm replacing pumps at an existing pump station. I want to make a good choice. I don't want to make oops, I put in a bad choice, or hey, there's pumps that are there that are just not working well. I don't want to make the same mistakes that were done before. What kind of tools do I have that are in there that can help guide me to make a better choice? Well, the system curve analysis is really the best tool that gives you that information so that I can make the best choice. Because why? It's very expensive when you make a bad choice or a poor choice for the pumps. I want to size them properly. I want to make sure they're going to operate well in their entire flow range of operations, whether in the ultimate design to when it's just one or two pumps running, all those kind of things. I want to verify the pumps aren't going to run in a place that's going to damage them or it's going to be inefficient. If I have a system curve, that's really going to help me do those things and do it well. So how does a person calculate a system curve so that I can actually do those kind of tasks, right? So you can use a model, a hydraulic model, to do that. And so you run basically a series of analyses from zero flow up to a maximum flow. And in there, in the model, you do that with the pumps off, and you put demands, positive demands on the suction node, and you put an equal and opposite negative demands on the discharge node. So it acts as a supply, and those are going to be equal and opposite. And so I'm going from zero up to my maximum, and then I just do intervals along the way. And the difference in head between those two nodes is the head that's required to push that flow that's in there. So it's actually ends up being a fairly straightforward and simple analysis, but that's essentially gives you the measure of, hey, how much energy is required to push this flow at this facility. And that's why a system curve analysis is a station analysis and not a pump analysis. And so that's kind of why it's important, to understand this. Hey, this is, you're looking at an entire station. Hey, I'm pushing flow in there, and that's why it's important to know that. But it's basically saying, hey, that head difference, when I do that, and by putting the positive demands in the suction node and the negative demands in the discharge node, you're going to account for the head loss on the suction side as the flows increase. And then, as you put the negative demands, it's going to act as supply. And in the model, a negative demand will say, hey, what head do I need in order to push this flow in there? And so it'll tell you, hey, the head difference, that's the energy that would be needed to push that flow in there. And so you can, that's what a pump be needed. That's the energy the pump would have to provide in order to do that. So it's going to give you that exact measure. That's what you need to know, you know. And so I can, mathematically or graphically here, we can kind of see this. Here's, again, our system, and, we're putting the positive node on the suction side, and we're putting the negative nodes on the discharge side. And then we're just increasing those from 0 up through our maximum flow, just incrementally a little bit at a time so that we can get a nice curve. And then that's kind of essentially how you do a system curve analysis. And so some key factors on there, again, we start with that, understanding that static lift, that minimum energy. Hey, before I started, 0 flow, what is that minimum energy that I have? So that's why, those curves were offset at 0. That's important to understand what that static lift is. Again, we talked about this already, that the analysis is on the station. It's not a pump analysis. Again, the head loss is going to increase as the flow increases. And that head loss is both occurring on the discharge side as well as on the suction side. Sometimes, hey, I don't have a whole lot of head loss on my suction side if I have just a tank right there, and that, that's kind of controlling the hydraulic grade line, so it's not varying much. I might only have a short section of pipe, or I might have a tank far away and I have a lot of pipeline, and so I could have a lot of head loss on my suction side. It can vary. Sometimes I have a little bit, sometimes I have a lot of head loss on the suction side, but almost always you're going to have a decent amount of head loss on the discharge side because I'm pumping to a receiving tank most of the time, or pumping to my far customer and I need to maintain some minimum pressure for them, kind of thing. That's usually what's governing in all those. And then lastly, again, remember that, hey, because those suction and discharge, conditions can change, that can create some family of curves. And so, hey, again, that question, how do I identify those family of curves? Hey, I know they're there, but how do I do that? Because if those are the magic curves that I need to do, well, what do I do? How do I find it? And so generally, if you think about it, where is going to be that highest system curve? Well, in the max static lift, which would be when my suction tank is at its lowest level and my receiving tank is at its almost at its highest level, that would be my maximum static lift. And with no demand in the system where I'm pushing all the water to the tank, because that would be the most resistance to flow, because all the water has to go through all the pipelines. There's no demand to peel it off on there. That's going to be the most head loss that the pipelines would be pushing up against. That's going to usually end up being in most cases your highest system curve. What's the lowest system curve generally is going to be your minimum static lift, where, hey, my suction tank is at its highest level and my receiving tank is at its lowest level. And then I've got my highest system demand, so that system demand is actually pulling off water whenever I'm trying to push it in there. And that's helping me, as well as kind of also reducing that minimum static lift even below what that minimum static lift is, because even before, when I start pumping, water's coming from the tank and getting some head loss before it gets to the pump station. So it actually lowers it below even what the minimum static lift is. It actually is dropping it below that slightly. So it's actually even helping me. And then, hey, as I'm pushing water into the system, it's actually going to the system demand until the system demand is being satisfied. And then the rest of that water is going to go up to the tank eventually. But that's oftentimes a lot where that lower system curve is, and again, in all these things, and then a lot of times with all the other pump stations on, but hey, don't take my word for it, on those, and again, in your system, you want to double check everything, because, that, can be different. But, just to kind of illustrate, hey, here's the maximum, static lift, where you're at the lowest level here to the highest level, or the minimum, I'm at the lowest receiving to the highest, just to kind of illustrate those minimum max static levels, and again, why are those important? Because, hey, if I do get those boundary curves, all the other system curves are going to fall in between, and if the pumps work at those boundary curves, they're going to work in between, right? And the only place, the pump can operate is along the line of the pump curve in between my maximum and minimum curves. So, it can't operate above, it can't operate below, it can only operate in between, which is cool. And so again, just as a caveat, don't take my word for, hey, this is always the maximum, this is always the minimum. You need to always do your due diligence, and evaluate your system, because there can be, differences or odd things that can occur. So always, double check and say, hey, let's look, let's think, and let's put our engineering cap, to make sure we're capturing truly our highest and our lowest curves. But, in general, those are things that do make sense and are probably going to be pretty close to where your minimum max curves are, but double check it. Don't take my word for it. Okay. Here's some examples of this. Is actually an analysis I did many years ago. Doing that same thing myself. Hey, what are they? And let's look at this. Let's look at this. And finding, hey, look, these are, what they are, and it does kind of make sense. What that maximum would be, and what the minimum would be. But again, always verify it. Don't take my word for it. So you can see on there. But when you do get the boundary curves, you will definitely find that all the other system curves are going to fall in between. And so that's really the magic here, is that, hey, once I find those, then everything else falls in between. And so that's why it's important, is to know that there's a family of curves, and B, that I need to find the maximum, and I need to find the minimum. And that's really one of the key things. If you say, hey, what do I need to find, and how do I do it? So how do I run that, in the model here? So, hey, I'm going to have to select a pump in the model, even though it's a station analysis. I still have to select a pump because of just the way the model tool works. Because it says, hey, okay, give me a pump to run it on. I have to tell it, hey, do I want an exponential or a multi-point type of curve? Because that's kind of the shape that it assumes, whether it's just draw straight lines between it, or I assume that's exponential in shape. How many points do you want to run? I would recommend at least 10 minimum. And it's going to do some key assumptions here. It's going to assume that all flow goes through what pump you select. The max flow that the system curve is going to do is it's going to project the pump curve for that pump, where that pump curve, if projected, where the head on that pump curve, when it projects it out, is going to be down to 0 head, that maximum flow. Obviously, it's not going to generally run a pump that far out, but if mathematically you project that out, where that head goes to 0, that's where it's going to stop the system curve. So just, this is how the tool works. And then whatever your current system conditions are in the model, where you've set up, what are your demands, what are the tank levels, whatever's running, that's the conditions that will apply when you run it. So then it's going to run a series of steady state runs from 0 up through that max flow, where that pump head is projected to be at 0 head. And then it's going to put a positive demand on the hidden suction node of the pump. So remember, in the EPNet engine, pumps are line elements, not point elements like they are in Infowater Pro. So, there's a hidden node that you don't see in the model. That hidden node is where they put the positive demand, and then the hidden discharge node is where they put the negative demand. Okay, so and then basically they do that analysis. Hey, here's the positive node, positive demand on the suction node, the negative demand on the discharge node. They get the head difference. They plot all the points and the pump curve, and lo and behold, well, actually, I'll show you what it looks like in the next slide. But here's what your tool would look like in the Run Manager. So you're on the System Curve tab. You select the System Curve tab. You select the pump that you want it to run on. You select that curve type. You select the number of points that you want to run. You can choose different times. However, generally your system conditions for different times aren't going to change too much. So if you did choose different times, you're going to see those are very close to one another. So generally, I'd recommend just choosing a specific one, or run it on a steady state condition, and then you just run the model. So that's basically the points, and these will be in the slides that you can get in here so you can see it. But this is what it would look like. so it's going to show you your pump curve projected out to zero head, and then this would be your system curve, that it would say, and you can see that it's going to run to there, because that's often what people say, hey, I've got a 4-pump station, it didn't run far enough because it, how come I wanted it to run farther, and this is why sometimes you need to do what we call like make a kind of a virtual or a dummy pump that's on there, because, if you think about, like, here, I've got a little pump station drawing here. And if I chose one of these real pumps on here, these piping, for the actual single pump might be undersized to push all the flow for all the entire pump station, as well as this pump curve, when it's projected out, might be not enough flow to represent all the pumps in the pump station. So those two things together, I might be getting too much head loss due to these smaller pipes, and I might need to make a virtual pump that's maybe sized the same size as the header piping, so that those, because these are sized to handle enough flow for the entire station. So I can make my dummy pump, with pipes connected to it that are, sized the same size as the header, so that I know, hey, those aren't going to cause excessive head loss, which can be a problem potentially. And then 2, I can make sure the pump curve for that virtual pump is representative of, it's a combined pump curve for all the pumps in the station. How do you do that? You take a 1-pump curve and you keep the same heads and multiply the flows times 2. That would be a 2-pump curve, flows times 3, a 3-pump curve, et cetera, et cetera. You can make a 4 or 5, as many pump curve as you need, and use that for your representative dummy pump or virtual pump, and then run your system curve using that one. And that's often, one of the little tricks that you can do so that you can get that system curve to run out far enough, as well as not have too much head loss to the connected pipes that are on there. Obviously, because this is a station analysis, you do also want to make sure all the other pumps are off. So their initial status is off, and there's no controls that turn those on. Because if they do turn on, that's going to kind of mess up the analysis. So might be a good idea to, potentially inactivate the pumps and the connected pipes for those other pumps in the station. That's one easy way to do that. Or you could just, give them the initial status and potentially, turn off the controls. That's another way to do it. But, sometimes it's just easier, in my opinion, to just, hey, let me temporarily make these inactive, and then I don't have to worry about turning those all back on. Whatever's easier for you, you always can do that. But just keep that in mind. So that virtual pump, definitely something to keep in mind. And then again, because your boundary conditions are essential, it's a really good idea to set up a couple of scenarios. You're going to at least need 2 runs, right? Because you're going to have your upper boundary curve and your lower boundary curve. Probably a good idea to set up 2 separate scenarios, so that I've got one scenario that I ran for my maximum system curve, and then one scenario for my lower system curve. That way you can always go back if there was a problem, you need to rerun it. You don't have to go and make all those changes and do that. It's just easier. But again, it's really up to you, but that's what I recommend. So now I've got my family of system curves. I ran all those, I've set those up. Now let's use that to actually do something. So, for instance, hey, I've ran my system curves, I've got this, and now I want to use this to choose a pump. So how would I do this? So obviously, I would probably do this in Excel, because you need to have, the system curve tool itself is only going to give you one system curve at a time, and you really need to look at this with both system curves and your different pumps. And so it's not really easy to do this in the model. It's much easier, in my opinion, to just take all this data that you get from the model, pop it into Excel, and do your comparisons there. Very simple and easy to do that the way I always used to do this. But once you have both your maximum system curve and your minimum system curve, you're going to need to identify, if you've got a couple of different pump choices, you're going to want to overlay your 1-time, 2-time, however many pumps are at the pump station, so you can have pump curves for the one-time pump curve, 2 times with basically it's a 2-time pump curve for when 2 pumps are running, 3-time pump curves for when 3 pumps are running. This is kind of why you don't really run a system curve for, you know, 1 pump and then another pump, because it's really, you're just overlaying where the 2 pump, 3 pump, 4 pump curves look like, and where those pump curves intersect those system curves is really where those pumps are gonna run, you know, and that's why it's a station analysis, not a pump analysis. But once you get those, then, you know, you're gonna say, hey, now let's look at where those are. Let's look at the efficiencies at those points where they're intersecting on those curves. And I can make some decisions on, hey, are these operating at good efficiency points on there? And if they are, then, you know, and if I'm deciding between pump A and pump B, I can make a choice of, hey, this is a better efficient pump, or this is this than this one. And so I can make some informed decisions, you know, of which one is going to be a better choice, you know. And let's look at a graph here, because this will kind of explain, you know, what I'm saying here of this lower third. What I mean by that, it's kind of hard to explain that without looking at this graph here. So when I talk about that, you know, I'm overlaying here, I've got my maximum curve and I've got my minimum curve in red here. And you can see I've got, you know, 1 pump in this first one in the blue, and I've got the second one in red, the 3 pump curve in green, and the 4 pump curve in purple right there. And you can see in between those 2 lines is the only place the pump is going to run. So, you know, above the green line, the pumps will never run, and below the red line, the pumps will never run. They're only going to run on the lines in between those 2, you know, maximum and minimum system curves. And pretty much on the lower third, so closer to the red line, is generally where most pumps are more often going to run. Why is that? You know, generally because, you know, think about it, you know, where do most pump controls turn on? Hey, when the tank gets low, turn on, right? So what is that lower system curve? Hey, it's higher demand when that receiving tank is its lower operational level. So that generally in that lower third part is where if you know, you look at your historical usage in that lower half, the third of that curve, is probably more often than not where you're going to see most pumps really typically operating, you know. And so if I really want to maximize my efficiency, kind of where we show in that little red circle is probably, you know, going to be probably a better spot, you know, than in the upper part of the curve towards the green, where it's not as often that I'm probably going to have those no demand and I'm pushing all the water to the tank, you know, kind of things. But, you know, looking at, you know, hey, all these things where I've got 1 pump and I've got 2 pumps, and 3 pumps and 4 pumps, I want to look at that entire things together. Incidentally, if you look at this, like, hey, it's a 1 pump station, you know, if this is probably like a 2,000 gallon a minute design flow pump station, and then if you look out for, you know, hey, when 4 pumps are running, I'm not getting 8,000 gallons a minute. I'm getting closer to maybe 5. You know, why is that? And that's because that system curve is increasing, you know, and that's why you know, that's typically what you're going to get. You're not going to get exactly directly additive, you know, hey, if this is a design 2,000 gallon a minute pump, when I do 4 of them, I'm not going to get 8,000 because of that system curve, and it's scaling up. That's why. And the system curve would tell you that, you know, but that's why that happens. And you can see that directly on the system curve because that head loss is increasing. That's why as you add more pumps, you're not going to get quite as much. It's going to get slowly less and less per pump as you add it because of the added head loss. And it's just going to show you that directly on the system curve, and you can see that, which is pretty cool, you know, that, oh, that's why, you know, and that, you know, because you can often see that and you know that, but you can actually see it directly on the system curve. It'll tell you that, hey, this is why you're not going to get that 8,000 gallons a minute. You're only going to get 65 or 67, you know, or something like that, you know. But so now when you do that, you know, hey, I can look at that. I can look at all those operations. I can look at, you know, hey, what's on there. The key things that you want to keep in mind, though, is don't get just fixated on the ultimate system design. You know, a lot of times we're looking at, you know, hey, this is a maximum conditions, and I want to maximize this for its ultimate design. And I'm looking at that, 3 or 4 pump, if it's a firm capacity, this might be a 4 pump station, but I'm really designing it to, hey, 3 pumps are what I need for that, because my fourth is my, my spare in essence, so hey, what's it doing for 3 pumps? And I'm kind of maybe getting a little bit blind about what's happening with 1 or 2 pumps, and I'm not paying as much attention for that. But you want to be really careful about doing that, and definitely looking at historical operation of, hey, how are they really operating it? Because especially when you get in a 4 or 5 pump station, you may be missing the maximum amount of operating time that they're actually running most of the year. Hey, if 50% of the time I'm operating with only 1 or 2 pumps, and only maybe 15 to 20% of the time or maybe less, I'm operating at that maximum capacity. And I might be missing, hey, maximizing the efficiency in those lower conditions. I might be missing some very important things. And so it's really important to, make sure you take a look at the whole big picture, and you don't miss, just focusing in on the ultimate, and missing, oh yeah, there's other things that are going on, and I need to take a look at that, and I think everybody's probably seen this. This is kind of an example. I can definitely tell you in here, I've seen more than one pump station where one has been designed and they've been so fixated on the number 1 point, and they failed to look at the number 3 point, and the station really operated much more often at the number 3 point, and the pumps that were selected for the number 1 were very appropriate for number 1, but they were terrible for number 3 point. And so ultimately the client wasn't happy because they used the number 3 point mostly, and the pump station that comes to my mind, they only operated, it turned out in this situation, only at the number 3. So it's always very important also to definitely, when you're designing anything, to, hey, what are you really going to use this for, right? Because sometimes, hey, I need it for this, but then I really only want to do this, and so sometimes that's why it's good to make sure you understand the design criteria. But even when you're doing that, to make sure you look at everything, because if you fail to look at, if you don't do a system curve, you definitely can miss this. You can, oh my gosh, look at operating point 3. That's terrible for this pump. Like this would be horrible if they ran it this way. Oh, this pump is going to be, it's just going to be so unhappy, and it's just going to be, and that's exactly what happened for that situation. And so no one wants that to happen. And so if you don't catch anything else, definitely catch this. Hey, when I do any kind of pump selection, this is why this is important. If I fail to do this, I'm really putting myself at risk of missing very key important things. And so this is why this is so important, and because this will tell you, hey, you're missing something important, and why I need to look at the efficiencies at point 3 and at point 2 and point 1. I need to look at everything, not just the one ultimate design point, but at all the points, because if I don't, I'm probably putting myself at risk and missing some key points. And especially when we get to the end and we look at the SCADA data, you can see in that station how often they were much more often operating at points 2 and 3, and very rarely operating at point 1. And it's just like, holy cow, look at that, and man, we can get so fixated sometimes in that ultimate design, you can, oops, and nobody wants to have the oops, right? And so that's why that's important. Okay. So I'm just going to briefly go over this closed zone thing. This is also covered in the other presentation slides, but just some key things here, because we get a lot of questions on this. Closed zones, like I said, you have to run these manually. You can't use the system curve tool because of a couple of things. One is because the first point that's run in the automated tool is at 0 supply. Well, in a closed zone, there's no tank, right? So the only supply is coming from the pump. And if there's no supply, then my demand isn't satisfied, and the model just can't handle it. As well as whenever you do this analysis, supply and demand have to be perfectly balanced. If they're not, the results are not going to make sense. So, that's something that just the tool itself can't handle it. It kind of expects, hey, that, you've got, you know, a tank, and most of the time that's what you've got, and that works perfectly, and it works awesome. But if you've got a closed zone, you can't do that. So you have to do this manually. You also have nothing that's telling it what the hydraulic grade line is. So you need to add a dummy pump, just a hydraulic, something to control the hydraulic grade line on the discharge side that should have no supply in or out of it. And that's one of the checks that you do, but you can see, these slides and go through here and we can talk about it. But, in essence, you just run kind of an EPS run where you come up with a pattern that increases the demand from 0 to what your maximum demand is. And we have a little spreadsheet that we can send you. Basically, it's sent as is, so you have to check the calculations yourself. But it can help you create this pattern. It can help you take the results of the model and see what your system curve is. But that to help you do this. But basically, you're going to put all that pattern on all the demands in your closed zone, put that same pattern on the suction and discharge node. Then you just run a quick analysis, and we show you kind of here's what those the time steps would be. You just run it for like 14 minutes. All the other demands in the system, you basically give it a constant demand so that it keeps it close to baseline conditions that are on there. You kind of want to set up, its own demand set to do this. And then you just want to do a check to make sure there's no flows in and out of my little dummy tank that I put on there. If there aren't, then you know that, hey, I summed up my demands in my closed zone properly and I perfectly balanced them. That's kind of the point to that analysis. And then, hey, the head difference between my suction and discharge node, that's going to be my system curve. You can't quite get that 0 point, but you get as close as you can. And usually that's close enough. But the only last thing that we wanted to point out is generally that's a little bit of an iterative process. In a closed zone, sometimes you have a couple of points that you're like, hey, I have a point out here that, hey, I'm going to need 40 PSI for this customer, and he's my highest elevation point, or he's maybe my farthest customer, whatever your key pressure is. That's usually what you're doing here. Hey, I've got some kind of pressure criteria that I need. And so either he's my highest elevation or he's my farthest customer away, and I've got some minimum pressure. And so that's usually what you're using to set the HDL in that dummy tank. Like, hey, I want that. That's what it's going to be, and so, hey, that's what he needs. So that's what I'm going to shoot to meet. That's kind of what you're doing there. But I'm not sometimes not sure, hey, is it going to be this customer or this customer that's going to end up controlling? So that's kind of what that iterative process means. Sometimes I might need to do that one and check it against this one. And then in essence, what you're trying to do is find out, hey, based on those two customers, which one is going to end up having the highest pressure needed at the discharge of the station, because almost without fail, most of these are going to have a variable speed pump discharge on the pump station. And so once you identify that, running the system curve with the tank at those 4 customers, you're going to then do a third system curve with the tank at the discharge at the pump station, putting the tank right there. That's going to make your system curve as flat as a pancake, because there's no, it's going to always be right at that discharge pressure. However, I at least know, hey, this is the HDL that's needed at the max flow to maintain whatever I need at my farthest customer at the highest demand. And then I can use that to give a, hey, this is what the discharge pressure should be set at that variable speed pump station. I can know that, and then I can use that system curve to evaluate different pump choices. Even though, like I said, your system curve can be flat as a pancake. It's not going to be a very exciting system curve, but then but that's the unique factor. And again, that system curve, or sorry, that Excel spreadsheet is kind of what it looks like, that we can send you, and it's got instructions, and those those detailed instructions that we usually will send people that ask for it. This is kind of what they are. They'll be in the slides so that you can actually see it, and it kind of goes through, hey, here's what we recommend. Here's what's there. You can take this, that little spreadsheet, you put your closed zone demand of what it is in there, your sum through demand 1 through 10, what the total demands are. You put that value here. I know what my maximum demand that I want to run my system curve out to. I put that here. It'll actually create a pattern for you. That's how you can put that in your model. And then you run your model with those time settings that you had, and then you can copy the result from your suction node and your discharge node and paste it in there, and it'll actually put your system curve right there. So, just so you can see that, and it's got those instructions, as well as those time settings on there so that you can see that right there. Okay, so now let's go into a couple of other additional things. So this is really cool, this little pump curve tool that's actually in the model that will actually help you. Hey, now if I'm troubleshooting the model and I want to see, now that I understand, hey, what system curves do, and remember, where does a pump operate? It operates where the pump curve and the system curve intersect, right? So even if I don't have a system curve and I've got a model that's acting strange, I'm like, why is my pumps operating too much, or why are my pumps, flowing too little? I can use this pump curve tool to see where on the pump curve the pump is operating. And if it's operating, away from generally a good spot on the pump curve, I usually, that's unusual. And I can usually say, hey, there's something strange. Why is it not operating in the typical spots of where a pump should be operating? And I can investigate why. Okay. So let's look at where the typical spots that a pump should be operating and why they should be. So generally, if you look at a pump curve, right here, this is kind of the general shape of a pump curve. Most of the time, the best efficiency points on a pump are going to be in this range on a pump curve. And let me just go to the next slide to just kind of show you that. This is a real pump curve, and there's 3 different impeller sizes here. And so you can see, I'm not making this up here, in terms of, this is generally, they are, roughly this kind of 2/3 of the way. And this is generally where you would expect your best efficiency points, your design points. If you have a pump curve that's generally operating roughly in this range, that's kind of where you would expect it to be, and so, if you're looking at this graph, generally you'd expect it to be somewhere in this range, right here, that, hey, that's probably fairly normal, and if it's way too far over here on the left or way too far over here on the right, that's probably a little strange, and something that should be potentially investigated, because anything that's way far over to the left, anything that's near shutoff head, generally is a little strange. There's probably something unusual going on, something that's forcing the system curve to make the pump operate way far to the left here, or in many, maybe I have something strange going on with my pump curve, but something odd. Or hey, if it's operating way far over here on the right, that's also very strange. And so definitely should, what I call, people's modeler sense, almost like, Spider-Man would have his spider sense, go off like, ooh, something isn't right here. Your modeler spider sense, should be tingling here. Something isn't right. I should check this. Something just doesn't feel right when you see something operating here or here. And this pump curve tool you can do will plot, and it'll actually give you a point that'll show you, hey, where is your pump currently operating right now? And so when you see it operating in strange spots, you'll be like, that's strange. Let's investigate why. Okay. So we already talked about that slide. So here's how you get there. Okay. So in your output, report manager, you can go under your graph report and you can select this pump curve. So when you say, hey, run this pump curve graph, it's going to have you select which pump you want it to graph. Okay. And so you just basically browse to the pump that you want. And then once you select it, then it's going to bring up this graph for that. And any hours that the pump is operating, you'll see this little blue dot. And that blue dot will represent, hey, that's where your system curve, your current system curve at that hour is intersecting the pump curve. And that's really cool because, you know, again, I don't even need my system curve because that's telling me right now, that's the active system curve where it's intersecting. That's where that pump is running, you know, and so that, you know, hey, now I've got a better understanding of system curves and what they mean. That's why that pump is operating there, right? You know, and so and it's always going to project out your pump curve, you know, just like the system curve does, even though, you know, hey, I don't have a pump curve that goes to zero head here, you know, but why it's going to show that. So even if you've got a multi-point, a design point, a 3-point exponential, no matter how, it's going to project it out to zero head, you know, so know that, you know, because sometimes you're like, hey, well, my pump curve doesn't go out that far. That's why it's going to look that, you know, so you have to be aware of that, you know, because sometimes you might be like, hey, I really, you know, my pump curve's up here, you know, that's fine, you know, and sometimes I'll actually go back and look at my pump curve first in the actual definition, and then I'll go back and look at this graph just so I know where that pump curve graph stopped, you know, on the pump curve definition, you know, just so that I know, hey, what is the last point on that curve? Because sometimes that's important because like design point curves, their highest flow point actually is 2 times the design flow at zero head, you know, which really stretches out the pump curve. But, you know, knowing how to get to this curve and being able to see it, you know, can help you. So, you know, let's say, hey, I have a pump station where my pumps are pumping too little, and I'm trying to figure out why that is. You know, I'm comparing it to SCADA data, and I'm getting way less flow out of this station than I should. And you know, what should I be looking at? You know, this is, you know, and I graph this and I'm saying, you know, I'm looking at the pumps and they're operating pretty far to the left. And I'm like, why are they doing that? Well, possible thing to explore would be, you know, because things that would make the system curve push it to the left would be, hey, is there low suction, right? Is something causing the HCl on the suction side of the pump station to be low, because that would increase that static lift and push that pump to be operating to the left on its curve. Is something causing the discharge head to be unusually high? If it is, that also would cause the system curve to, you know, have a higher static lift and push that pump to be operating to the left. You know, so these are things, you know, hey, just things to check, you know, so that you can use this and it helps you go, what's on it? You know, obviously, is my pump curve defined well, you know, because if they're not, you know, that's good things to know and good things to check, you know. Same thing if my pump is flowing too much, it's just the opposite, you know, hey, is my suction head too high? Is my discharge head too low? You know, it's the opposite, you know, and then I can find that and I can investigate it and go back and look, you know. So these are all good things to go in and check. So lastly, let's just go in and look at the SCADA data, how you can use that to validate your pump curve data. You know, it's very fantastic tool. This is also in that original system curve presentation. So I'm just going to go over this quickly. You know, essentially, if you know your pump TDH, that's your discharge head minus your suction head. So how do you get your discharge head? You almost always have a discharge pressure sensor. So that pressure, you can convert that pressure to a head 2.31 per PSI plus the elevation suction head. If you have a tank that's controlling that tank level, basically plus its elevation is going to give you your suction head. Or if I have a suction pressure, then it's just like the discharge pressure, that gives me no suction head. The PDH is basically the discharge head minus the suction head, right? And then I almost always have the flow. And so then I can plot the total dynamic head plus the flow. And so then I can get my point so that I can see what's on there, you know. And so if I do that and I plot all these points that are on there, I can get a graph kind of like this. So I can see, hey, here's my system curves, here's my pump curves. I can use this to actually validate my pump curve. So hey, if I'm seeing some differences, I can actually adjust my pump curve down to match those points, you know, that are there, which is really nice. As well as I can also see where are my pumps operating, which is really valuable person who actually gave me this data and allowed me to use it when we did the system curve presentation actually took 2 or 3 years of their data and was actually had some peak data on here. So they were like, man, I could really see my pumps were really operating here and here. And this is kind of what I was talking about, man. If this was my ultimate design, you can see how few points are really out here compared to just the number of points, you know, way down here. And so this is why sometimes you might want to say, hey, I'd really need to give maybe a little bit more look at maximizing the efficiency at these points, especially if I'm operating way more here, might be more important to do that, and why these points and how you can use this to help guide you. How we operate. Don't take my word for it. Don't take this word for it, but actually use this in your SCADA data so you can take how we operate, and you can actually do that. You know, and then if you want to use this to calibrate, you know, your pump curve data, this pump curve digitizer again is one of those as is Excel spreadsheets. If you're interested in that, we can send you that to help you to digitize your pump curve. But you know, you can also take this and then use this to adjust your pump curve down based on the pump curve to best match those SCADA points that you have. Again, that's the question, so we can go to those now. You know,
Yeah, so with about 5 minutes left, thank you so much, Patrick. This was great. So we have a few questions that folks asked. The first one being, do the min and max system curves function similarly to VSP controls on a pump?
No. The min and max system curves essentially are going to be, you know, looking at, hey, energy wise, what is the, you know, looking at any system, you know, what is the maximum amount of energy that is going to be, you know, based on the system conditions. You know, if you had, you know, what are the system conditions that would create the most energy required to pump water into the system, and then based on the boundary conditions, what would be the minimum energy to push water into the system. And so
got it. And then, Patrick, do you mind moving the mic a little bit down, because the voice was faint at the end? Yeah, and then there was another question on, if you're choosing specific times, does the model run EPS until that time, and then does the system curve calculation? So when you're doing that system curve analysis and you pick a specific time, does the model do an EPS in the background?
It's going to do a number of steady state runs at the time that you select. So it's going to choose, you know, whatever hour that, you know, you're on, and go back to that slide here. So, you're going to choose like whatever hour that you choose right here. It's going to go to that hour, and then it's basically going to do a bunch of steady state runs at that hour.
Got it. And then someone was asking, is there an easy way to see the pump curve graphs for all the pumps and not selecting by one?
Like for the pump curve tool?
For all the pumps that they have, can they view all the pumps on one graph superimposed on the system curve? Or would that need to be, you view one pump at a time?
Well, you obviously have to do the system curve analysis one pump at a time, because it's, you know, one station at a time. You know, I mean, you can do like the PZM tool, you know, which I cover in the other presentation, you know, which allows you to kind of show, you know, hey, I want to look at different combinations of pumps and see that, and you kind of can see the system curve as well, and kind of show you different combinations of things, which I think is really handy, you know, for doing that. That's probably the easiest way to do that if you want to do that. But I didn't cover those slides in this, but in that other presentation, we kind of show that.
Well, and then there was another question on, you know, running, when you're trying to do the system curve analysis to develop your system curves, would the wiser option be running 2 steady state scenarios with the demands and initial conditions to represent min and max, or would you recommend the 24-hour EPS and select the peak and min hour?
I'd definitely run it as 2 steady state runs. Absolutely. Because in essence, too, because of the you almost have to, because to get those boundary conditions, it's almost impossible to get that in a 24-hour EPS run. You almost really can't, guarantee. And that's really what you want to do is say, hey, I definitely know this is my system conditions that are going to be my maximum. This is definitely going to be my conditions that are my minimum. If you chose those in an EPS run, you're really not guaranteeing that you're doing that, and that's the problem with that. I mean, you might be getting something that might be close, but you're not really guaranteeing that I'm getting those maximums. So it's safest, in my opinion, to do two steady states where you're setting those up where I know that I've got the boundary conditions exactly the way I want.
Excellent. And then a final question is, do you size pumps differently in one station to address the 0.3 and 0.1? Remember when you had the curves for 3 pumps running, 2 pumps running, 1 pump running? Do you size pumps differently in one station to address those points, or is it just you're using one pump and just multiplying it, as in having parallels running at the same time?
Gotcha. So these, like you're talking about, these slides here.
Yep.
So that's just taking the one pump that you're choosing, because a lot of cases, especially, you're usually nowadays, going to put in the same size pump. Doesn't mean you have to. There can be times where you may, certainly have, especially if I've got something where, hey, I've got some unusual conditions on the low end, and maybe this is way too far out in the future, and so I need, I've got just something that, hey, this isn't going to be efficient enough, and I need to account for something, or, hey, it's just is not going to work well for this. These work great out here, but they don't work great here, that I might need to do something, different there. But again, it's just why you need to look at it, but in essence, this is just, hey, with the same pump, multiplied 1, 2, 3, and 4, because that's most often what you're going to be looking at. But it doesn't mean that's the only thing you can look at, but that's just, hey, whatever you're proposing, that's what you'd want to lay out.
And we're right at the hour, so this pretty much wraps up the water talk. But thank you so much, Patrick, for an excellent presentation and taking time out to go through the questions. And if anyone has any questions, please feel free to reach out to us via email or call us at any time. And yeah, thanks again for joining our water talk, and we'll see you at the next one.